Okay, hi, my name is Sarah, and I am going to be presenting part D of the Proton Mass project alongside of Kishan. Um, so here we have our two questions. This is my question over here on the left side, and Kishan's on the right. The way we have the slides labeled is each slide is actually going to have our question on it. My slides will have a circle with this color, and Keyshawn's will have a circle with this color, and each circle will have the actual question in it. So for my question, how much energy is required to accelerate a proton to 10% of the speed of light, and what does this reveal about the relationship between mass and relativistic kinetic energy? So how does this question connect to the group project? So it builds directly on our topic of proton mass by showing how mass affects the energy needed to accelerate a proton at high speeds. We talked earlier about what a proton is, its mass, and where it's found, and now I'm applying that in a real-world physics scenario. Instead of just naming the mass, this question asks, what does that mass actually do when you try to move the proton really fast? And it connects to particle physics and experiments showing why proton mass matters in energy-related calculations.
Hello, I am Keyshawn Cantu, here with the continuance of the Proton Mass Project. This is part B. So my question was, how much kinetic energy does a proton gain when accelerated through a 1 million volt electrical potential difference in a particle accelerator? This question focuses on proton mass, but looks at how that mass is involved when a proton is moved using electric fields. It connects to particle acceleration, which is a major real-world use of protons in science labs. It uses the charge and mass of the proton together, showing how both play a role in how much energy is gained. It's a practical application of the physics behind proton movement and supports our overall project theme.
Why is solving this question important? It helps explain the difference between classical and relativistic energy. Most people know about kinetic energy, but this shows how much more energy is needed when something moves close to the speed of light. These kinds of problems are used in labs and accelerators, so it connects to real careers in physics, and it gives a better understanding of why mass and energy are deeply connected and how we apply that to actual science problems.
The reason why it's worth solving is because it helps explain how electric fields are used to give particles energy, something done all the time in particle accelerators. The formula used is super important in physics and engineering, so learning to apply it is valuable. It shows how energy, voltage, and charge all connect, and how those things depend on the particle's mass. This gives a hands-on way to understand physics beyond just reading it in a textbook.
How I landed on this question. So I first thought about how using regular speeds and the basic key formula, but that felt too simple. So then I considered going really extreme, like 99% of the speed of light, but that math got way too complicated. So I settled on 10% of the speed of light because it adds just enough challenge without making it impossible. And it was also hard to find the right balance, but I think this question fits the project well while also being interesting to solve.
So, I went through various steps of creating my question. I originally thought about calculating energy for a proton just moving at a basic speed, but that didn't involve anything new. I wanted something that had or that was tied into electric fields since that's a huge part of how particles are accelerated. Using a 1 million volt potential difference made the problem realistic but still manageable to calculate. I tested a few versions before landing on this one, and it ended up being a good challenge without being too overwhelming.
What makes my question stand out? So most problems stick with the basic KE, but this one goes beyond that with relativistic kinetic energy. It makes you think about how much energy increases as speed increases, not in a straight line, but more dramatically. It's not just about solving a formula, it makes you reflect on what the answer means and how it applies to real world science. and that's what makes it stand out from the usual textbook problems.
This question uses a real-world concept, electric potential energy, which is often used in experiments but not always explored in class. Most problems just give speed or mass, but this one adds voltage and charge into the mix. It's realistic since accelerators you actually use huge voltages to move particles like protons. It stands out because it ties mass, charge, and energy together in one meaningful problem.
Visualizing the energy needed for high speeds. So I made a graph comparing velocity as a percentage of the speed of light to relativistic kinetic energy. It shows that energy increases slowly at first but rises drastically as velocity increases, even just at 10% Cs. The proton's mass stays the same, but the energy needed grows non-linearly. This visual helps explain why particle accelerators need so much energy even for small mass particles, and it gives a better understanding of how mass and speed interact on a deeper level.
I made a table showing how voltage affects the kinetic energy of a proton. The pattern is linear. The higher the voltage, the more kinetic energy the proton gains. At 1 million volts, the energy gain is noticeable, but still within realistic lab values. This helps visualize how particle accelerators use voltage to control energy levels. It gives background for understanding how charge and electric fields affect proton motion.
Breaking down the formula. So, for my question, I used the relativistic kinetic energy formula. Each part of this formula has a specific meaning. The m is the mass of the proton. It's really small, about 1.6 times 10 to the negative 27 kilograms. The c is the speed of light, which is a constant at 3.00 times 10 to the 8th meters per second, and gamma, and that symbol, which is also called gamma, is a number that adjusts based on how fast something is moving. It gets larger the closer the object gets to the speed of light. I found gamma using the equation that we're seeing on here. For my case, since the proton is moving at 10% of the speed of light, gamma comes out to about 1.005. This formula tells me how much energy is needed to move something small like a proton at speeds where normal physics formulas don't work as well anymore.
This was the math for the formula I used. And so this shows the direct relationship between the voltage and energy when accelerating charged particles like protons.
So solving it step by step. So now that I had all the values, I had just had to plug them into the formula, um, which you can see right here. First, I did gamma minus 1, which was 0.005. Then I multiplied that by the mass of the proton and the square of the speed of light. After doing the math, the answer came out to approximately 7.5 times 10 to the negative 13 joules. That might look like a small number, but when you're dealing with something as tiny as a proton, there's actually a lot of energy. It shows even at just 10% the speed of light, you already need a significant amount of energy to accelerate it.
So this is how I solved it. It's a short calculation, but it represents what real accelerators do. It gives a measurable energy gain that helps us understand the power of voltage in manipulating protons. And just like in Sarah's problem, this amount of energy looks small, but it's powerful when applied to tiny particles like protons. This is the kind of energy gain we see happening constantly in real life particle accelerators.
Double checking the answer. So, some ways that I double checked my answer: I checked the math using online tools and got the same value, around 7.5 times 10 to the negative 13 joules. This makes sense based on known calculations in physics. Energy increases rapidly as we approach relativistic speeds. The answer is small but important. It shows that mass directly affects energy even if the particle is tiny, and it connects perfectly with our project on proton mass, showing how it matters beyond just being a number.
This answer is consistent with known examples in textbooks and online sources. Proton kinetic energy values from high voltage fields usually fall in this range. The result makes sense when comparing it to Sarah's. Hers was higher because of the velocity. This one is based on electric field energy. Both answers together give a full picture of how proton mass interacts with different types of energy.
Cool facts we didn't fit anywhere else. So, the proton's mass was first measured in the early 20th century, and it took decades to refine it to the precise number we use today. Protons are incredibly stable. They have a lifetime of at least, um, that's a typo right there, this number, to the race to 31 years, which is much longer than the age of the universe. Proton accelerators, like the large Hadron Collider, can move protons close to the speed of light to study fundamental physics. And scientists still study tiny differences in proton mass because it affects our understanding of the universe's structure.
Also, proton accelerators rely heavily on electric potential differences, like the one in this question, to increase energy in tiny steps. Protons are used in medical applications too, like proton therapy for cancer treatment. It takes extremely high voltages to make protons gain significant energy. Just 1 million volts is small compared to actual accelerators.
So, what surprised me the most? I was shocked by how tiny the energy gain looks in numbers, but how big a difference is when you get close to the speed of light. I didn't realize how much the math would change when switching from basic kinetic energy to relativistic energy. It surprised me how much real world science, like particle accelerators, is directly connected to what we're learning here. And if I had more time, I'd love to dig deeper into how particle accelerators measure these energy changes to so precisely.
Working as a group with fewer people was challenging, but it did help us stay focused. The hardest part for me was making sure my question tied back to the bigger picture. The easiest part was solving the math once I had a clear problem. Overall, I think our questions really worked together and made this project stronger.
Our project in a nutshell. So, overall, the project helped me see how proton mass isn't just a number, it affects every calculation in particle physics. The hardest part was probably making questions that were challenging but still solvable. The easiest part was finding background information. The tough part was using it in a meaningful way. And I'm proud that we each came up with unique questions that complemented each other and told a bigger story. So here are a few of my sources. Um, and here is my visual. Um, so this is a source where I found the formula I used to solve my problem. It shows the full relativistic kinetic energy question, which is Ke equals mc squared times gamma minus 1. This formula helps calculate how much energy is needed to move something really fast. In my case, a proton going 10% the speed of light. I used this version of the formula because the regular kinetic energy equation doesn't work well when you're dealing with speeds close to the speed of light. And this screenshot helped me understand what each part of the question means and why I needed to use it for my question.
So, this is the source where I got the formula I used to solve my question. It shows that electric potential energy is equal to charge times voltage. That's the relationship I used in the form Ke equals QV to figure out how much energy a proton gains when it's pushed through a 1 million volt potential difference. In this case, all of the electric potential energy gets converted into kinetic energy, which is why this formula works perfectly for my problem. This helped me understand how protons gain energy in particle accelerators.